Mass spectrometry is a technique that ionizes chemical specimens and sorts the ions based upon their mass-to-charge ratio. More simply, a mass spectrum measures the masses within a sample. Mass spectrometry is used in many different fields and is applied to pure samples as well as complex mixtures. A mass spectrum is a plot of the ion signal as a function of the mass-to-charge ratio. These spectra are used to determine the elemental signature of a sample, the masses of particles and of molecules, and to illustrate the chemical structures of molecules. In a typical mass spectrometry procedure, a sample, which may be solid, liquid, or gas, is ionized by bombarding it with electrons. This may cause some of the sample's molecules to break into charged fragments. Those ions are then separated according to their mass-to-charge ratio. The ions are detected by a mechanism capable of detecting such charged particles. Results are then displayed as a spectra of the relative abundance of detected ions as a function of the mass-to-charge ratio. The atoms or molecules in the sample can be identified by correlating known masses to other identified masses through a characteristic pattern. X-ray diffraction is a technique used to identify phases with a crystalline material. It can provide information about the unit cell dimensions of a material. It turns out that crystalline substances act as three-dimensional diffraction gratings for electromagnetic radiation in the X-ray spectrum, just like prisms do for light. The spacing of planes in the crystal lattice of a material acts as a diffraction grating and allows researchers to determine the shapes of the lattices and thereby determining the compounds that make up those lattices. X-ray diffraction is also used to determine the shapes of larger molecules, including vitamins, drugs, proteins, and nucleic acids such as DNA. Electron microscopy utilizes electrons rather than photons to create an image. The method is capable of much higher magnifications and has a greater resolving power than a light microscope, allowing researchers to see much smaller objects in finer detail. A scanning electron microscope, or SEM, is a type of electron microscope that produces images of a sample by scanning the surface with a focused beam of electrons. The electrons interact with atoms in the sample, producing various signals that contain information about the sample's surface topography and composition. The electron beam is scanned in a special pattern used to code for visual displays, and then the beam's position is combined with the detected signal to produce an image. SEM can achieve a resolution better than 1 nanometer. The transmission electron microscope, or TEM, operates on many of the same optical principles as the light transmission microscope, just at a much higher resolution. For example, you can study small details in the cell or different materials down to near atomic levels. Since electrons are very small and easily deflected by gas molecules, it is necessary to use the electron beam in a vacuum. Instead of glass lenses focusing light in a light transmission microscope, the TEM uses electromagnetic lenses to focus the electrons into a very thin beam. The electron beam then travels through a cross-section of the specimen you want to study. Depending upon the density of the material, some of the electrons are scattered and disappear from the beam. At the bottom of the microscope, the unscattered electrons hit a fluorescent screen, which produces a negative image of the specimen with its different parts displayed in varied darknesses according to their density. The image can then be studied directly by the operator or photographed with the camera. The scanning tunneling microscope, or STM, images surfaces at a 0.1 nanometer resolution. With this tiny resolution, individual atoms within materials are routinely imaged and manipulated. The STM can be used practically anywhere, in ultra-high vacuum, air, water, and various other liquid or gas ambience, all while at temperatures ranging from near absolute zero to over 1,000 degrees Celsius. STM is based on the concept of quantum tunneling. When a conducting tip is brought very near to the surface to be examined, a bias or voltage difference is applied between the two, which allows electrons to tunnel through the vacuum between them. By monitoring the current as the tip's position scans across the surface, a program can model an image from the data.
Mechanical testing of materials under various load and environmental conditions gives information on the properties and characteristics of the material. Measurable parameters include ductility, fracture toughness, elongation, hardness, impact resistance, strength, and stress resistance. There are many different methods available to test materials for these parameters, such as compressive, bend, hardness, impact, and tensile testing. Knowing this information is critical for deciding what materials are best suited for which applications. Compressive testing characterizes the behavior of materials subjected to compressive loads, helping to determine a material's yield strength, failure mode, service life, and other critical performance characteristics. Flexural bend testing measures the behavior of materials such as strength and ductility when it is subjected to a simple bending load over a given radius. A material's strength is measured by determining its resistance to penetration and indicates how easily a material can be machined, how well the material will wear, and if treatments and coating may be needed for the performance desired. Material impact strength is determined by fracturing a notched specimen and measuring the amount of energy absorbed by the material during fracture. In tensile testing, a varying load is applied to a test sample up to the point of failure or predetermined criteria, creating a stress-strain curve showing how the material reacts throughout the test. The data provides information about the tensile strength, strain, modulus, and ductility of the test material. Kapow! For particulate samples, particle size is one of the most important physical properties. The size of a particle has direct influence on properties like reactivity, stability in suspension, texture, flowability, viscosity, packing density, porosity, and dissolution rate. Two of the most popular methods for determining particle size are laser diffraction and dynamic light scattering. Laser diffraction works by measuring the angular variation in intensity of light scattered as a laser beam passes through a well-dispersed sample. The angular scattering intensity received is then analyzed to calculate the size of the particles responsible for creating the scattering pattern. A volume distribution is obtained, which shows the volume percentage of particles at a given size. Dynamic light scattering is usually used to measure particle size of materials in the submicron region. Particles that are in suspension undergo Brownian motion caused by thermally induced collisions between solvent molecules and the material particles. When the particles are illuminated with a laser, the intensity of the scattering light fluctuates over time at a rate dependent upon the particle size. Smaller particles are displaced further by the solvent molecules and move more rapidly. Analysis of these intensity fluctuations yields the velocity of the Brownian motion and hence the particle size using the Stokes-Einstein relationship.
Thermal gravimetric analysis is a method of studying material reactions under controlled temperatures and atmospheres. A TGA test measures the change in weight percentage of a material as its thermal and atmospheric environment changes. The final results of a test are able to display differences in weight percentage and compositions of the tested sample to examine how it reacted to the given temperatures and oxidations. The data from a TGA test allows researchers to easily visualize how the sample responded as temperatures changed, which gives them a good understanding of the material's physical and chemical properties, such as the compositions of what materials exist, what this material could withstand, and how it will react to different conditions. Optical microscopes, often referred to as light microscopes, essentially utilize ray optics to enlarge images of small sample sizes in order to observe the fine details of a microstructure. This method uses lights and lenses to reveal light patterns through a sample material, which is then examined to find changes in light intensity and different transmission or reflected angles of light to distinguish the characteristics that the material holds. As useful as optical microscopes are, they can only see down to a resolution of 1 micrometer. Two main optical microscopes are the reflected light microscope, which reflects light off of the sample, and the transmitted light microscope, which passes light through a thin microstructure. Reflected light is used for opaque materials such as metal, while transmitted light is used to study translucent materials. Between the two, transmitted light microscopy achieves maximum illumination and therefore a more accurate study of the microstructure is obtained.